So we have a periodic motion problem today. A block of mass m is attached to a horizontal spring with force constant k. It is moving with simple harmonic motion of amplitude a. Calculate how much of the energy of the motion is kinetic at x equals 1/4 the amplitude. That's part A. Part B states if one adds a mass smoothly in a vertical drop at x equals a, calculate what happens to a, t, and omega. So this might seem fairly difficult at first, but all we need to do is do conservation of energy, relate this to a few other equations, and it becomes fairly straightforward. Down here is a good drawing of what's going on in part A. Always recommend when you're doing a physics problem, draw a picture. It can really give you a lot of detail as to what's happening. So I'll demonstrate how to set this up. You have your total energy equals your kinetic energy plus potential, just conservation of energy. And we know that for a spring system, your total energy is going to be equal to 1/2 Ka squared, and your potential energy is going to be 1/2 Kx squared. But wait, we know that x equals 1/4 A. So we can just toss that on in, and then we would end up getting, okay, I believe that would be 1/16th, no, 1/32nd Ka squared. Yeah, because you take 4 times 4, it's 16, multiply that by 2. Yeah, that should be it. So you have 1/32 Ka squared. So let's actually plug these into our equations. So we have 1/2 Ka squared equals the kinetic energy plus 1/32 Ka squared. All right, so then we solve for kinetic energy at this point, which we can see is going to be 1/2 Ka squared minus 1/32 Ka squared. We can factor out the Ka squared, so then we would have Ke equals Ka squared times 1/2 minus 1/32. In order to solve for that fraction, we just do a common denominator. Multiply both those by 16. You'll have 16/32 minus 1/32, which is equal to 15/32. And so then you have 15/32, and that's going to be equal to your kinetic energy. So your kinetic energy, therefore, because we factored out the Ka squared, that's going to be 15/32 Ka squared. So that is the solution to part A. Okay, so I hope that made sense. We just used conservation of energy in order to rearrange our equation and solve for the kinetic energy by solving for x at 1/4 of the amplitude. Okay, so that makes sense. Let's move on to part B. And part B wants us to find out what happens to the amplitude, the period, and omega, the angular frequency, I believe it is. What happens to those if you add a mass? And we're going to assume that this mass is greater than 0, because that's typically how mass operates. So it's a greater than 0 mass. So we first want to find out what happens with A. So we just solved for our kinetic energy, which is going to be really useful for this portion of the problem. So we have 15/32 Ka squared. And luckily, we also know that kinetic energy is equal to 1/2 mv squared, because that's one of the major equations of kinetic energy, and just energy in general. So we know that that's true. So let's just get rid of that and figure out what A is here. So we solve for A. I'm going to try to do this best as I can. So let's see. 1/2 mv squared So you'd end up having 32 times 2, which would be 16 mv squared over, that should be 15k. And then, of course, take a square root. It's going to be 16 mv squared over 15k square rooted. Perfect. So now we're going to write the equation with the mass added to it. So we have 16 m plus little m v squared over 15k. So out of these two, which of these is bigger if m is greater than 0? Well, obviously, since it's in the numerator, this value is going to be larger. Since this is the value that we're using, assuming that we've added a mass to this object and just solving for the amplitude alone. So the amplitude, since this gets bigger, amplitude gets bigger. So that's what happens to A. So moving on, we also have to solve for t and omega. I don't recommend solving for t first because that's going to get a little more complicated. We should definitely solve for omega. So we know that omega, the angular frequency, is equal to k. What am I doing? The angular frequency is equal to k over m. I mean, if you think about it, an omega is basically an upside down m, but I wouldn't think about that too hard. So we also have k over big M plus little m. This is the one that we're using to assume that a mass has been added. So which one of these is bigger? Well, when you make something bigger in the denominator, it makes the whole expression bigger. That's why if you have, 1 over infinity, if you take that limit, it's going to go to 0. And if you have, 1 over 0, which is technically undefined, but I'm making this more into a limit, you get infinity. So if it's getting bigger, that means that we're going with this limit, so that means that this gets smaller, indicating that this is larger. So then our omega gets smaller. Okay, so I hope that makes sense. We're going to move on to t. So if you remember, the period is equal to 2 pi over angular frequency. Let me just check that real quick to make sure that I'm on the right track. Yeah, that's what it is. Okay, so that means we can set that equal to 2 pi over the square root of k over m. And so now we can multiply this. I see what we got here. So if we remember, we can also set this up as 2 pi over the square root of k over big M plus little m. Okay, so this is where analyzing this gets a little more complicated, but if we remember, this whole thing here is equal to omega. So we know that when we add that m, our omega gets smaller. And if we take a limit as something gets smaller in the denominator, the entire expression gets bigger. So if that gets smaller, that means that the whole expression gets bigger, indicating that this is greater, and t, our period, gets bigger. So that's your answer to part B. I hope that this made sense. Basically just relating it to a few other equations. If you need to, just when you encounter a problem like this, just look through any equations you've got. See if you can find ones properly relating it to things like amplitude, things like its position, its kinetic energy, whatever you can find, and just doing your best to form exactly what happens. In this case, we needed to relate it to mass. So I hope that makes sense. Stay tuned for more of these in the future.